Hey everyone, welcome to day one of 6.1, and the title is Antiderivatives. Some of this should seem kind of familiar to you, some of it's going to be a review. So we're going to start off today by just doing a quick review of things that we've already done from last chapter. So if I'm going to find the integral or the antiderivative of 5x dx, we know that you need to add a power onto the x and divide by that power. And then we are evaluating this problem from 0 to 4. So we're evaluating the results. Substitute 4 in, substitute 0 in, and subtract, and you would get 40 as an answer for this one. And so you do the same thing, with each of these over here. So this integral would be negative 2x to the third over, I don't know why I wrote negative. Let's erase that. Positive, 2x to the third over 3 plus x squared over 2 minus 3x, and we are evaluating from negative 2 to 2. And if you were to do all the work and substitute 2 into each x and subtract what you get when you substitute negative 2 into each x, you would find that this answer is negative 4/3. And I want to take all the time to work all of that out. Okay, and then this one over here is best done if you, at least I think, if you rewrite this as 2x to the negative 2 dx. And so this antiderivative becomes negative 2x to the negative 1, or if you like, negative 2 over x, and evaluating that from 1 to 3. And when I substitute 3 in and then substitute 1 in and subtract, I get a final answer of positive 4/3. Okay, so those are all ones that we should have been able to do last chapter. So now we're going to talk about these three problems at the bottom. So I hope you're noticing what's different about them. They are different because they do not have any bounds on the problem. So these three problems, as of yet, you can't evaluate, you can't get a whole number answer for. These are called, aside from antiderivatives, are also indefinite integrals, meaning you don't have definite bounds. So it's kind of like when you take the derivative of something like 2x squared. So just want the derivative of 2x squared. But I'm not asking for the value at any particular point. I just want to know the expression. So we are going to be using rules to solve these problems that will also have expressions as answers. Okay, so we do have some rules for these. The thing I want you to understand, though, is what's different with the antiderivative rules is that you are missing like what could have been a constant at the end. So that means that you want to think of the fact that every problem, you'd have an infinite number of answers that would differ by a constant. So hopefully some of these will look familiar to you as I show them. So the integral from x to the n dx, that's what we would consider the power rule. So you're adding 1 to the power and dividing by that power. And then, of course, you're adding on that plus c. And the main thing to notice about this one is that that should not say x. I'm struggling today. This should say n cannot equal -1 because you can't have 0 in the denominator. Okay, now we are on to the problem where actually the power is equal to -1. So you could actually rewrite this problem and think of it like this, the integral of x to the -1 dx. So here, this problem on the left said n cannot equal -1. In this problem, this is the example of when n does equal -1. So the antiderivative of 1 over x is the natural log of the absolute value of x plus c. All right, next one, e to the kx dx, the integral of e to the kx dx. The rule for this one is e to the kx divided by k plus c. You can see a lot of division stuff going on. Remember, what you're trying to think of is what original value or what original expression, so this is the original expression, what original expression gives me this thing as its derivative. Okay, moving on. The integral of sine of kx dx, again, k is a constant, would be equal to negative cosine kx divided by k plus c. Should kind of lead you to what the next one's going to be. The integral of cosine of kx dx is equal to sine of kx over k plus c. So again, basically we're saying the derivative of sine of kx over k is equal to cosine of kx. The integral of secant squared is tangent x plus c. The integral of cosecant squared x dx is negative cotangent x plus c. The antiderivative of secant x times tangent x dx is just secant x plus c. And the integral of cosecant x cotangent x dx is a negative cosecant x plus c. Okay, so they're not really things you have to memorize now because you kind of already know them. You memorize them for chapter 3. So hopefully you remember that the derivative of secant x is secant tangent. And that means if you see the integral of secant tangent, you can go back to secant. So the goal is that you shouldn't have to do any more memorizing. Just think of it in the opposite order. Okay, so now we're going to do some practice problems. So these are all indefinite integrals. So we're going to start off with a couple of problems that are power rule problems. These should all kind of line up pretty nicely with what the homework's going to be, or the classwork, excuse me, is going to be tomorrow in class. Okay, so x to the 4th becomes x to the 5th over 5. 2x to the 3rd becomes x to the 4th. You're dividing by 4, but there's already 2 out front, so it becomes x to the 4th over 2. And then this part is 3x. And whatever you do, don't forget your plus c. Yes, AP will take off if you do not have a plus c, and there's supposed to be one. All right, so now this problem is probably easier if you rewrite it as 3x to the negative 2. Get my dx. So 2x to the 3rd becomes x to the 4th over 4. But just like the other one, there was a 2 out front, so now there's going to be a 2 down here. And I am going to add 1 to a negative 2. This actually becomes a problem for people, so be careful when you add here. So this becomes 3x to the negative 1. And I need to divide by a negative 1 plus c. So this one could be rewritten as x to the 4th over 2 plus 3 over x plus c. All right, so there's our first two problems. The next couple ones I think aren't too bad. So secant squared of 3x. It is kind of a little bit like a chain rule here. So the antiderivative of secant squared is tangent. So this should be tangent of 3x. But then I have to divide by 3 because when I take the derivative of tangent of 3x, you would do the chain rule and there would have been a 3 out front. So you need it to cancel out. All right, and then number 4 over here. Remember, please don't forget to pause the video if necessary, take any notes, write down questions that you have as you go through. Okay, the antiderivative of cosine is sine, so this becomes 2 sine of x. And then this is cosine of 5x, which means the antiderivative of that is sine of 5x divided by 5, and then, of course, plus c. All right, moving on. So number 5, actually, we're going to have to do a little bit of like trig work on this problem. So I'm going to first rewrite this as the integral of cosine squared theta over sine squared theta. And remember, theta is just another variable. Don't let it freak you out. So here we are with that one. And I really wanted to have only signs in the problem or only cosines in the problem. I can't really change my denominator because then I have two terms in my denominator and I can't split it up. So instead, I'm going to change my cosine into 1 minus sine squared theta. So I'm using a trig identity, a Pythagorean identity, actually. So I have now rewritten this as 1 minus sine squared over sine squared. So that means that I can separate this into two fractions. So I have 1 over sine squared minus, and then sine squared over sine squared is just 1 d theta. So finally, I'm going to change 1 over sine squared into cosecant squared theta minus 1 d theta. And then I'm going to integrate both of these. So the antiderivative of cosecant squared, let's get back that color I was using, is equal to negative cotangent theta. And then the antiderivative of 1 is just the variable. So in this case, it's theta, and then plus c. And then don't forget, you could actually differentiate this to see if you get back to where you started. There is another way you could have done this problem. You could have actually done, like, changed the cotangent squared into its identity, which happens to be cosecant squared theta minus 1. You've done that at the very beginning and gone from here to here, so from this step to this step. But I know a lot of people don't remember that identity and are more comfortable with changing things into sines into cosines. If you remember it and you want to think of jumping from this red dot to this red dot, feel free. That would have been totally fine. All right, moving on to the next page. So now we're going to talk about differential equations. So a differential equation is an equation that basically has a derivative in it. Differential equations are used a lot in calculus, in particular in engineering. We will be focusing on what are called separable differential equations. There is a whole course in college called differential equations that will talk about things that are not separable. So that's something that could come later down the road, depending on what you are, like what your major is. Sometimes differential equations are also called initial value problems, where you're solving the differential equation given a specific set of data or a first point or a parameter or something like that. We've actually done these already, just we didn't focus on calling them this. Couple of things to notice at the top. There's a couple of different notations that you might see. Come back and look at them if you need to. All right, so here's our first differential equation or initial value problem. So you have this dy dx, and I want to solve for y, which means I need to get y by itself. So what I'm going to do first is I'm going to move the dx to the other side, like this. And then I'm going to integrate both sides. So I'm going to do just start off with an indefinite integral on both sides. This is like a 1 dy over here. So when you find the antiderivative of a constant, you're putting the variable attached to it. So this is like 1y or just y. And then 2x, when you integrate this, it's in terms of dx on this side. This becomes x squared. And then 1 becomes x. And then, of course, you need your constant. Okay, so this would be fine if I didn't give you an initial condition, and that's why these are called initial value problems. So you're given an initial condition that you're going to use to solve for c. So we're being told over here that on the original function, x is 2 and y is 0. So I'm going to put 0 in for y, 2 in for x, and solve for c. So this is 4 minus 2 is 2, I think, I hope. Therefore, c equals a negative 2. So far, so good. So then finally, you have to rewrite the actual y equation. So y equals x squared minus x minus 2. So this is the solution to this initial value problem or this differential equation. All right, so now I'm going to do another one where you're actually given the second derivative. So we're going to do this twice. So I have d squared y equals 2 minus 6x dx squared. I'm going to integrate both sides. So I'm kind of going to ignore that this is the second derivative for right now. And I think it's easier if I write this like this and write it as y prime. So when I integrate this, I get y prime as opposed to trying to just say dy. And then this is a 2x, and then this becomes 3x, 3x squared plus c. And then I'm going to come over here and say, oh, well, the derivative is equal to 4 when x is equal to 0. So the derivative is equal to 4 when x is equal to 0. So I get c of my derivative is equal to 4. So now I'm going to write the derivative. So let's go over here now. So y prime equals 2x minus 3x squared plus 4. So that's my first derivative. So now I'm going to repeat the antiderivative process again, knowing that this is like your dx portion over here. All right, so the antiderivative of the derivative would just be y, and then 2x becomes x squared when I integrate. 3x squared becomes x cubed. 4 becomes 4x, and I need another c. So if these c's get confusing and you want to call this c1, 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 and you want to call this one c2, if that makes you happy, you can. It's not necessary. But if that helps, you can do that. My initial condition for the original function is when x is 0, y is 1. So 1 goes there, then I have 0 minus 0 plus c2. So this c in the original function now is equal to 1. So my final answer is y equals, I think I'll go in descending order, negative x cubed plus x squared plus 4x plus 1. So this is the solution to this problem right here. All right, I hope this is making sense. We have one more to do. Well, kind of two more, but I think I might stop after the next one and see if you can do the last one on your own. All right, so this one is actually kind of a physics problem. So some of you might already know how to do this just purely because you've seen these types of problems in physics. Let's see how it goes. So a ball is turned upward with with an initial velocity of 64 feet per second. So this is literally v of 0, or v naught, is equal to 64. And it's thrown from a height of 80 feet above the ground. So that would be your position at time equals 0 is 80. Okay. Then the question is, when does it hit the ground? And then you're given this little recall from physics that the acceleration, which happens to be the derivative of velocity, is negative 32 feet per second. So we are going to think of a of t as the second derivative. So I want the integral of a of t, and this side is equal to negative 32. And we should call it dt over here on both sides technically. So the antiderivative of a of t is v of t, because remember that, again, acceleration is the derivative of velocity. And this is negative 32t plus c, I'll call it c1. And now is when this initial velocity condition is going to help out. So when time is 0, velocity is 64. So 64 goes here, 0 in for time. So the constant for the velocity function is 64. So therefore, my velocity equation is negative 32t plus 64. Okay, so now I'm going to use that equation and use it to come up with the position. So we are going to find the antiderivative of the velocity, and we know that velocity is equal to negative 32t plus 64. dt goes here. All right, so the antiderivative of the velocity is the position, so s of t. Negative 32t becomes negative, this should look familiar to you physics people, 16t squared plus 64t plus c. And we know that the initial condition for the position is when time is 0, the position is 80. When time is 0, the position is 80. So my constant for the position is 80. So my final answer would be negative 16t squared plus 64t plus 80. All right. Finally, I did say that I wasn't going to go over this last one with you, but I think I'm going to at least get you started thinking about it and see if you can come up with an answer on your own and we can talk about it tomorrow. Okay, so this is the third derivative, so I'm just doing this problem 3 times. So I am going to think of it as y triple prime is equal to x to the negative 3. So if I were to find the antiderivative of both sides of this would give me the second derivative, and the second derivative would be equal to, we're adding 1 on, dividing by what I get when I add that 1 on, and now I have my first constant. So then I'm going to take this first condition and substitute it in. So y is equal to 2 when x is equal to 1. So when x is equal to 1, I get negative 1/2 as that value there. So my first constant is equal to 2.5 or 5/2. Okay, so that means my second derivative is equal to, I'm going to leave it with this negative power because I need to have it that way anyways. So negative x to the negative 2 over negative 2 plus 5/2. So what you're going to do now is find the antiderivative of both sides. And when you find it, you'll use this initial condition to come up with the c value, and then you're going to repeat it. I'm going to give you the final answer and see if you can get there, because I think the final answer, you might be surprised if you actually get it right and then would think you did it wrong. So the final answer looks like this. Y equals 1/2 times the natural log, the absolute value of x, plus 5/4 x squared plus a negative 1/4. Now, if you try it and you disagree with me, please let me know tomorrow so that we can go over what the answer is supposed to be. See you tomorrow.